So my name is Samuel Weston. This is my presentation from my master's project through the GIST program at University of Arizona. I focused on utilizing viewshed modeling and automating that process along with fire analysis techniques to find the best possible locations to place fire watchtowers in following the High Park fire in Colorado. So a little information about fire watchtowers, also known as fire lookout towers, before we start. First used around 1910 after a string of devastating fires. They decided there had to be some way to determine these fires are happening prior to the devastation getting past a couple hundreds or thousands of acres of burned land. They were wooden or metal structures with a viewing platform. The fire finder was the first primitive technology they put in. You can see that in the lower right-hand picture. Essentially was just a little circle with a map on it, had coordinates in it as well, and you were able to put a pin on the location of where there is smoke column or possible flames that you can see to alert emergency response teams. Those were used up till the 20th century, and now we use different technology like binoculars, radios, cameras, GPS systems. So a little presentation overview of what to expect. We'll go over the objectives, where the study took place, methods and data on how I plan to do the study, and the results that I found, and a little discussion towards the end. So the first objective was to just analyze the fire in general to determine the fire burn boundary and the severity and how the vegetation reacted to it. Next, we're going to look again, maximize visibility in a location for a best possible placement of those fire watchtowers. And then finally, just automate that process as it just a one click and let it run as opposed to small, tiny analyzations along the way. So the study area is, again, the High Park fire. It's just west of Fort Collins, Colorado, occurred in 2012, burned for almost a month. It was the second largest fire in Colorado history, a little over 87,000 acres burned. And the vegetation was just a normal forest. It's a mountainous region. It has conifers, pines, shrublands, various brush. The elevation takes into play a little bit later on in the process, but you can see the maximum lumens there. In the state plane Colorado North meters, coordinate system was used to just keep things consistent. Starting with the normalized burn ratio, how to use Landsat 7 satellite data, because that was what was being used back in 2012. The combination of the bands were bands 4 and band 4 used, or 7 used. And the equation is to the right. It's a simple equation. You're subtracting the near infrared from shortwave infrared, dividing by the sum, and then you're able to get pre-fire and post-fire normalized burn ratios. You subtract those two NBRs in order to get the difference, and then you reclassify them into the values to the lower right-hand side. And you can see if the area was high severely burned with low possibility of vegetation regrowth in the future, or if it has a chance of regrowing because it was unburned or just less severely burned. These are the raw reflectance bands, just showing the different images that were added and subtracted and then divided. They take different reflectance depending on the types of materials that are on Earth's surface. For the normalized different vegetation index, very similar concept, how to use Landsat 7 data, just different band combinations from the NBR. Again, Landsat 7 satellite was back in 2012. For today, we had to collect data using Landsat 8, and very similar equation, same concept, just different band combination. Again, similar to the difference NBR, the difference NBI takes pre-fire NDVI and subtracts it from present day, which was actually done in March 2020. Next, we have the digital elevation model. This was very important to use because each cell holds the observer point, which is a possible area for a fire watchtower. Each point holds an elevation data, and I had to focus in on the fire ignition point to sort of refine the study area a little bit more. And a total of 19,422 observer points. So it was a large process to conduct. 30 by 30 meter resolution just means if you're standing in one of these sites, just imagine a 30-meter box around you, 30 by 30 meters, and that's what we're working with. So to automate this process and make it run smooth, I had to create a model through Model Builder in ArcGIS. It iterates the observer points one after the other and creates a viewshed for each individual point, instead of having to go through the viewshed tool each and every single time for the 19,000 points. And I displayed the fuzzy viewshed tool as well. Didn't have to iterate these features because I only needed the top couple of viewsheds. This one uses that Euclidean distance tool in order to find out the distance. The further out you get from your center observer point, the less you're going to see due to environmental factors and such things that are going to diminish visibility over the distance. And I had to use a radius of 12,500 meters because the human eye can't see forever. Eventually the horizon drops off. This was taken by weather reports in the past couple of years. I just took the average of how far you were able to see on a normal day. The viewer offset was 24.61 meters. This is just adding the average height of a human, which is 1.75, plus the average height of a fire watchtower, and that's where your eyeballs are going to be looking out over the landscape. The first viewshed was binary, 1 point for visible, no points for not visible, so they won't even display. And each output was exported to Excel spreadsheet, and then I had to use Python in ArcGIS to add all the spreadsheets together to better analyze it, which is shown on the right. This was just easier to organize the data and go through things to find the top couple of viewsheds. At the very end, a total viewshed was created. I essentially added every single viewshed together to get an idea of what points share common visibility and what points just aren't visible across every single viewshed that was completed. The normalized burn ratio, you can see these deep red and deep maroon areas were severely burned. The burn scar is very apparent from this fire. It was quite devastating. The majority of the land was severely burned, and there were some valleys, some rivers and streams that made it out with less burn severity, and the vegetation we'll be able to see grow back a little bit better than normal. So this pre-fire NDVI shows that high vegetation index, those highlighted portions in the bright green and bright white. Those are good reflectance off of healthy vegetation. And we can see post-fire, it's a lot different story. That burn scar is very well outlined now, and we can see a lot of the vegetation was affected after this fire. Post-fire from, again, March of 2020, this is when the actual images were collected. You can still see that burn scar. It's healed a little bit, but it's still not back to where it was prior to the fire even beginning. And the difference NDVI shows the same story. This really isn't showing burn land, it's just showing the change from pre-fire to present day data. This first binary viewshed, again, very simplistic type of viewshed. It just gives the points highlighted in that gray is what you can see. And then if you can see clear to the base map, it's just not visible at all. So the top 10 viewsheds, I found the maximum visibility was 34.165%. And it slowly drops off viewshed after viewshed until you get down to the 2%, 1 percentile visible viewpoints. Most of those points were very, very low elevations in your valleys, stream areas. And what I thought was interesting, to the right-hand side, we have a different image. This is zoomed in on that digital elevation model raster. Each of these squares is a 30 by 30 meter cell. So the ranked from 1 to 10 is those viewsheds ranked, and they were clustered. It wasn't one single point with maximum visibility. It was more of just a general area, and it slowly trailed off from there. The fuzzy viewshed, again, gives you an idea of how your eyesight diminishes over a distance. The deep blue towards the center observer point, which is that red triangle towards the center, that's where you're going to be able to see more clear on an average day, a clear day. And the further out you get, different atmospheric hindrances will keep you from viewing things a little more clearly. And obviously something to the right, there could be a mountain, it could be a complete valley, is not visible at all, and that's why it doesn't hold any values. And the total viewshed, again, adds every single of those rasters together. So if a point of visibility is on top of another point in two different viewsheds, they're going to score as visible, and that goes over every 19,422 viewsheds. So the areas of the light blue going to yellow and red, very low visibility, not many viewsheds share the same visibility, and if you can see clear to the topographic base map, there's no points that shared whatsoever. And you kind of cool because it kind of contours to that topographic base map. So concluding this, a majority of the boundary was severely burned, and that was made more apparent by viewing the NDVI. It showed poor vegetation regrowth from pre-fire data compared to data taken from today. There might be some human interaction that may need to be necessary in order to get that vegetation index back a little higher from pre-fire numbers. We were able to produce that viewshed model, which again iterates over every single viewpoint, and that can be used in future studies. If you just take that tool, that model, and run it with different observer points, it will continue to just spit out those viewsheds, as many observer points as you had, and then further analysis can be done with those. Maximize visibility at the top observer point at 34.165%, and the max elevation of that specific point was 3,140 meters. Not the highest in our study area, but it's still up there. Obviously, the higher the elevation, the more viewpoint you're going to get, but that doesn't mean that it's going to be the absolute overall best visibility of that study area. And we also found areas that weren't visible at all. These areas may need some type of remote sensing techniques, whether it be dispatching drones to the area, cameras, or something down the future, in the future. to better analyze those areas in case a fire starts in those valleys. Then it's burned to hundreds of acres before we even see them and detect them. For some possible future studies, I would be curious as to see how human, again, intervention would help that vegetation regrow, whether it's hydromulching or aerial seeding, something to see if the numbers can be pumped back up with vegetation. Also adding buffer zones to primary and secondary roads. If these view sheds were to be, or these fire watchtowers were to be constructed down the road, you obviously need to get materials up there, and the easiest way is through some type of trail. And that would sort of help discover those best locations based off the buffer zone. And just discovering techniques to help with the automation process. Even though I still scaled it down and made that model in Model Builder, it still took a long time to process the 19,000 observer points. It took about a day and a half on my laptop. So maybe different techniques, different tools, tweaking it here and there to sort of find out how to make it run a little bit more smooth. So, and now I'm open to questions.